probably a good idea to go back and read Rolle's theorem before we have this discussion. If the function is continuous on the closed interval from a to b and differentiable on the open interval from a to b, and the endpoints y partners f of a and f of b are equal to each other, then there will exist at least one value c in the open interval of x values between a and b, such that the derivative evaluated at x equals c will be 0. And that is interpreted geometrically as a horizontal slope. So in this picture, you can see we've drawn the endpoints so that they are even with each other. In other words, the y partner to A, f of A, and the y partner to B, f of B, they're at the same height, the same level. So we have that condition met. We also have a continuous function on the closed interval from A to B. You don't see any place where the ant's going to fall off a cliff or fall through a hole. And then we have differentiability on the open interval from A to B because we don't see any spikes, abrupt turns, things like that. And no asymptotes, the function's defined. So the curve f meets all of the condition for Rolle's theorem. So the conclusion says there has to be a value x equals c between a and b that has a flat tangent at that point. So there has to be at least one x value, and we're going to call it c, between x equals a and x equal b, so that the slope of the tangent at that point on the graph is 0. In other words, the tangent line is flat. And that's how I've drawn it above in the picture. I have a dotted line for the tangent. Now, it would be easy for you to visualize this if you imagine nailing down a piece of string. The string is the function. Nail it down at the endpoints, and then move the string around a little bit. You can always pull the string up a little bit, and you'll get a flat tangent, or pull it down, and you'll get a flat tangent when you do that, as long as you can fluctuate and you don't have any openings or spikes on this thing. In other words, it's continuous and it's differentiable. Okay, so we will make sure that those conditions are met, and in those cases, you can see from the string analogy that you'll always be able to get a flat tangent. Now let's move ahead and think about the physical implications here. In the physical implication, the function f of x is called the equation of motion. It's actually the equation that describes the position of an object at time t or time x. And the derivative f prime is called the velocity of that function. We also call that speed when we're not concerned about the direction of the velocity. Okay, so let's think about this. Let's think about the physical implication. The physical application, so think of f of x as a position of the object. That means that f prime of x is a velocity of the object. If the function's continuous on the closed interval a, b, and differentiable on the open interval, and the position f of a is equal to the position f of b. In other words, the initial and final positions are the same. Then there will be some value x equals c between a and b. Now think time, and instead of an x value, you might think of t. So think of some time c for which the velocity will equal 0. You know, a good example would be to imagine an arrow shot up in the air. When it starts, it's at chest level. It goes up, turns around, comes down, and it ends its flight at the same level that it started. So f of a is equal to f of b. And if you drew a graph of the function describing the trip, the motion, you would have a function that's differentiable and continuous. And in that situation, if you had those conditions met, then you could be assured that there will be some value in the flight time from the beginning to the end at which you have a horizontal tangent. And that actually happens at the precipice, the very top of the motion before the arrow turns around and comes back down. For a moment there, the velocity is 0. There's an instant at the top where there is no velocity. It freezes for an instant. So I hope that helps you better understand Rolle's theorem.